to be here. Unfortunately, I can't attend the workshop. I'm happy to be here at the conference, and given the past presentations, I hopefully have brought a couple of slides that touch topics that people care, like energy injection scales, convergence, spectra. So all these are like there, and people who've seen me talking in the past know that I've cared a lot like about these idealized boxes. But I also brought something new today. So and recently I have been branching out a bit, and I'm now also looking at less idealized setups, and in particular, we've been looking or going towards AGN feedback in isolated galaxy clusters, because after the introduction from Marina in the morning, there are a lot of open questions, and I'm particularly interested in energetics. So we currently have a simulation program that specifically focuses on like how energy is being injected, deposited in the ICM. And there, like the main goal is to actually also like bridge scales from like small scales to cluster scales. But before we get there, let's go back to the very basics. I know I'm probably preaching to the choir here, but I think it's anyway for half of the talk, pretty important to remind everyone of like a couple of the fundamental incompressible hydrodynamic turbulence basics. And I will bring up these sketches on the right-hand side a couple of times. And particularly, there's probably no question about like the energy spectrum. So we have energy injection on the large scales, or maybe more. Then we have energy cascading down, and then eventually on the small scales, energy is going to be dissipated. From a numerical point of view, if we want to put this in a box, simulate this, there are multiple approaches to this, and we've also heard this in a couple of talks coming up. Some people talked about like DNS, so direct numerical simulations. And in these simulations, all the scales, starting from the energy injection scales all the way down to the dissipative scales, are exactly resolved. So they're directly numerical simulations. In practice, quite often, we can't cover all the relevant spatial scales, particularly in astrophysics with like very large Reynolds numbers. So what's happening in many codes that use like shock capturing finite volume methods, we talk about implicit large eddy simulations. And the implicit here means that we resolve the large scales, the large eddies directly, and we rely on numerical dissipation for handling like the physical dissipation that's absent in these approaches. So yeah, energy spectrum clear, and then if we translate the energy spectrum to how energy is being transported across turbulence, there's just like one way the energy can go. So we put the energy in here, and then in the inertial range, we do have a constant energy flux across scales that you can normalize to 1 if you like. And then at the bottom, if we look at how the energy is evolving at a certain scale, then in the stationary regime of turbulence in the inertial range, there should be no change in the system because energy is just transported across scales. On the larger scales, we do have an energy input, so there should be, for example, in our cases, large scale forcing, we put energy in, and then the small scales and the dissipative scales, the KD, energy is being removed, so there's also net change in energy. All right, so if we want to know a lot more, we can look at the energy transfers in the box. And we, a couple of years ago, extended an energy transfer analysis framework also to support compressible MHD simulations. What this means is that what you can see here in the movie is on the top left. This is all the scales in a sample simulation that highlight vortical motion in the box. Why we highlight vortical motion, you can see if we decompose or do the kind of like a shell decomposition individual scales, which results in eddies of various sizes. And then with the energy transfer analysis framework, we can actually calculate how all these different eddies at different scales transfer energy through different mediators. So for example, how energy is cascading down from like in the kinetic energy budget, but also how energy is being exchanged between the kinetic and magnetic energy budget, for example, through magnetic tension. And that kind of framework allows us to get a very like detailed view on the energy dynamics in these kind of systems. For example, also about like how the energy is transported across scales, but also how energy is being like scale-wise changing over time. So first detour, convergence. So we've heard about that, and even there's a big difference between hydro and MHD. So yesterday we heard that there's even for the same setup, MHD and hydro can converge to different states. So what we've done here, we have a box, subsonic, supragalvanic turbulence, just driven on the larger scales. And the only thing that we change is that we increase the box size, like we just put more and more spatial like cells in for the same setup. Start with 128 cubed, going all the way up to 2048 cubed. So what you can see here, kinetic energy spectrum, so extends longer and longer and longer. So you can say, well, this looks nicely converged. So all good, we have converged dynamics. Similarly, magnetic energy spectrum also, yeah, there's some differences here that may or may not be important, but in principle, all that goes down like with larger dynamical range, larger Reynolds number, so all looks fine. Good. So if you're, for example, interested in subgrid scale modeling, you could take this and say, well, we just do something in our inertial range here, we do a cut, and then we know how to separate scales, and we know what we have to model on the small scales. Unfortunately, it's slightly more complex in MHD, even for this like simplified setup. So with the energy transfer analysis, we calculated the cross-scale flux in these simulations, so how much energy is going from larger to smaller scales, across scales. All the lines from the previous plots, so all simulations are plotted here. We normalize our cross-scale fluxes in the sample to like 1, and you can see with increasing resolution, we just get a longer and longer point where like the energy is being energy transfer across scales is constant. So all good. Except when we now different mediators in MHD turbulence, the dynamics are now actually quite different. So on the left-hand side, you can see the kinetic cascade. So this is like energy going from the large scale kinetic to the smaller scales in the kinetic budget. In the center, you see like how energy is going from the large scale kinetic to the small scale magnetic budget through magnetic tension. And now with the different resolutions, or different dynamical range, different Reynolds numbers, these are all kind of like interchangeable, the dynamics change. So at the smallest resolution, like cross-scale flux is purely positive, and then with increasing resolution, we actually see that the dynamics change, and the kinetic cascade seems to be absent, or seems to be highly suppressed. And at the same time, if you look at the magnetic tension, this becomes stronger and stronger and stronger. So, and if you would consider what happens at a, like, say, given reference number, and you look at how the individual cross-scale transfers, like the ratios between them, this also changes with scales. So what that means is that for like MHD, is not only that the energy transfers are not constant, but they also depend on the scales that you're looking at. And this is like a pretty important thing to consider if you're thinking about, like, we want to do subgrid scale modeling, or we want to approach very, very large Reynolds numbers in astrophysics. What do you want to model? Do you want to model this term, or can you neglect that term? So therefore, it's a, my point of view, much open question what the asymptotic regime in these highly simplified setups look like, even if we're already at 2048 cubed, which is like not super big nowadays anymore, but still like larger than like many papers that currently built where theories are being built on. Well, one important point here is that these are all implicit eddy simulations. So you could argue, well, do you even do the right thing because you're relying on numerical dissipation to balance your energy transfers? Well, fortunately, the energy transfer analysis also allows us to address that question, because if we're doing that implicit large eddy simulation, as I said, like there is no explicit dissipation. So the energy in the box needs to go somewhere. Numerics does it. If we do the energy transfer analysis, we actually have like a residual. So this is now like how the energy changes over time, and on the small scales, we're expecting a bump here. We actually do account for the forcing, so there is no bump here. But we do have like a residual, too much energy that is not accounted for in these kind of simulations. And now A posteriori, we can calculate what like viscosity and resistivity should look like based on the flow fields in the simulation, and then just do a fit to recover the effective numerical and viscosity and effective numerical resistivity. So we did that. So we had a 256 cubed ILAS simulation, so that's a residual. We fitted that, we got numbers for the viscosity and resistivity. We redid the simulation at 512 cubed, which is now an ADNS and almost a DNS, because now we do the same analysis again, and the residual that was originally blue line here is now already much smaller, because now this term is accounted for in that simulation. And so we redid the same simulation again, doubled the resolution, and now we see that the blue line is gone, so the energy transfer analysis that now includes the explicit term is actually flat. And this means, in this case, like the dynamics are fully resolved because there's no leftover numerical dissipation that is not accounted for. So we reran a couple of these simulations and tried to, what do the spectral look like? What do the energy transfers look like? So we have that with 256 cubed from the previous slides, did this with 512 and 1000 cubed with the exact, or with the effective coefficients derived but reran. And now the spectra line up, and then the difference between these bunch of lines and those bunch of lines is just like a baseline 256 and a baseline 512 cube simulation. And in both cases, it actually works that we can say that our ILAS just represent a DNS simulation with the same effective coefficients, where we can actually determine the Reynolds number and kinetic and magnetic Reynolds numbers we're actually in, even though it's all purely numeric. This is a slide I already showed some time ago. So I said like it's a match. It's fine with the caveat for a given set of methods, because this was one point in parameters methods, or like for the set of methods that we used there. So last year, we had a summer student who expanded on that work, so don't look at the details, but the key point here is we really ran a suite of simulations going from Mach 0.5, Mach 2, Mach 8, sonic Mach number, and then we did numerical, varied the reconstruction method, first order, second order, third order, varied resolution, going again from 128 cubed to 1000 cubed. And in all these cases, first of all, we recover scaling in terms of the numerical, viscous, and resistive coefficients. But also you can see that the numerics behave slightly different in different regimes. So if you go to higher and higher Mach number, your effective coefficients go up. And this is, for example, attributed to the method because, for example, at Mach 8, with like a third order reconstruction, we do have to use like first order flux correction so that the simulation remains stable. And that is probably an imprint in effectively increased numerical coefficient. So therefore, now I can say like it's still a match, and actually you can apply that kind of method also to a broader set of methods and like physical regimes. And if you're interested in kind of like where in parameter space you really are with your given method, the energy transfer analysis does not rely on how you did the simulation. You can use any kind of data cube, throw that in, and do that kind of analysis also on your data if you're interested in. All right, so much for the idealized stuff. Let's go beyond ideal turbulence. As we referred in the morning, the ICM is a very dynamic medium. So their driving is not coming from like your artificial spoon or the monkey that Christoph showed the other day that's just like clapping to do like the compressive driving. No time left? All right. So we now do have like the more intermittent driving, like in this case from cluster mergers and AGN feedback, all that in a potential wall. So there's stratification, and we also have cooling, so multi-phase gas. It's all pretty much complex. And what you can see here on the right-hand side is one snapshot from our simulations, where we do have like a jet. This is here indicated by a passive scalar. And then there is like cold gas coming in from from a filamentary structure, which you'll also see more on that in a second. A little bit more on that simulation setup. So we also have a fancy abbreviation because apparently that's a thing that you have to do if you run a big suite of simulations. So we do exascale simulations of magnetized AGN feedback focusing on energetics and turbulence. So as I mentioned initially, isolated galaxy cluster setup, static gravitational potential, initial perturbations, and then we do have an AGN in the center that injects kinetic, thermal, and magnetic energy, and we let that evolve over time up to a total like 4 giga-years. As I mentioned, the emphasis here is on like energetics and turbulence, so therefore we put a lot of time/resolution also like in the central area. So we do have more than the 200 kpc cubed in that simulation covered by more than 2,000 cells. And the difference you can already see here, so that's like from a paper like from 3 years ago that has a very similar setup. So that's from a Perseus kind of initial conditions. And I tried to match the color map, and you can already see that there's like a lot more structure on like various scales that now is actually like resolved at fixed resolution. And to nail that home, like our actual box is like 6.4 megaparsecs, so it's going from here to here. And the grid structure here, every that you see has 128 cubed cells in there. So therefore, we really try to like get the center at high enough resolution to do some statistics. Just to briefly illustrate that, this is the evolution over time. On the left-hand side, you can see how the AGN is injecting power. The lines here indicate the magnetic fields that are evolving. This is like a passive tracer for the jet material. And in later times, you will start to see forming like cold gas that is streaming in mostly along like magnetic field lines. And if you look very careful, the magnetic fields line will also like become darker towards reddish, so they become stronger. So they're tightly correlated in terms of like the filamentary structure with a lot of like cold clumps going out, falling in. One other important point here is you can see that the AGN is going in various directions. There is no precession that's set up, so the jet is always completely aligned with the z-axis. And so therefore, like we do see these jets because they are deflecting from the cold gas that's falling in. So you don't necessarily need precession to get like jets that are not like always aligned in a fixed direction. So just last week, I managed to calculate an energy spectrum of like that central 2,000 cubed box simulation. Because everyone likes slopes, I also did some slope fitting. Disclaimer here, there probably is like a big uncertainty in these slopes because it's just a single snapshot, and depending on where you put the start and end for your fits, there could be some scatter. But the key part here is that on our energy injection scales, which is like around 1 kiloparsec, we do see something that looks like a Kolmogorov scaling. So the kinetic energy spectrum is in blue, the magnetic energy spectrum is in the green dash line. And then we do have a spectral break. There is another scaling here, which is flatter, which may look familiar to the idealized box simulations we had in the beginning, where we also had like a flatter than Kolmogorov slope. And so then magnetic energy becomes dominant on intermediate scales, which could, for example, be attributed to these extended filamentary structures that follow the cold gas falling in, because they give like structures that are larger, like on the 10 kpc scales, actually. So going back to the energy transfer analysis, this is my second to last slide. We do also analyze like the central box with the energy transfer analysis. Reminder for like the cascade kind of thing, we would expect that energy is trickling in from larger scales to smaller to smaller to smaller to smaller to smaller scales. So what you do see here is like an older plot from idealized boxes, where we have energy from like a single scale, where energy is coming from and where energy is going to in the sub and the supersonic regime. And all the data here is completely aligned along the diagonal, which really means like energy coming in from here, going there, here, in, out, in, out, in, out, in, out. Nice cascade all the way through the simulation. We now did the same analysis on like the AGN, like one of the simulations, one of the snapshots in the simulation. And What you now actually see is, first of all, again, we do have a cascade on the smaller scales, so energy in, energy out, energy in, energy out. Then we clearly see where our energy injection scale is at 1 kpc, and then if you look carefully, you can see the color swapped here. So now we do have an inverse cascade because the AGN jet is actually depositing energy on large. So this is like, I was very excited because I didn't expect what to see, whether this kind of energy transfer analysis actually works on like the more non-idealized setup. But at least this gives me some confidence that there may be more interesting stories to be told by running the full analysis on these kind of setups, but this is all like work in progress. And with that, I would just like close by saying I'm very curious to see where we are with respect to MHD turbulence, particularly is there an asymptotic regime, which we'll hopefully being able to address and answer soon. And also I'm very excited to now be on the path going from idealized boxes, like bridging the idealized setups with less idealized multi-phase simulations. Thank you.
Thank you very much. Thank you for the wonderful talk. Philip, please go ahead, Matish.
Quick comment and super quick question. So in 2021, we saw quite a bit of cold gas at different times. So it's a very much a statement that is time dependent. If you look at different times, there will be way more cold gas than on the particular slide that you showed. So it really depends when you look at it or how you look at it. How long were the simulations, your simulations evolved for?
In total 4 years.
Okay. So there's enough time for gas to be thrown out and then come back.
Yes, and actually, if you look carefully, so we some of the cold gas is even forming while still going out. So there's like multiple cycles, and so we do have like histograms also with the radial velocity and temperature, and you can see that it's not only like cold gas forming in, but actually the gas is cooling while it's being thrown out from the jet.
Thank you.
Let's go ahead, Irina.
Thank you. Really cool simulations, and I have a lot of questions, so maybe we can chat after. Quick clarifying question: if you go back to power spectrum calculation, it's a particular snapshot, or is it time average?
Yes, this is just one snapshot. This is like and I'm actually very curious to see how this matches with like the movie over time when you have like different jet activity and different amounts of cold gas. So yeah.
Yeah, and you're calculating here, you're taking all the velocity from the entire box.
Everything.
You're not excluding jets or anything, just everything. Okay, thank you.
But I'm like the next thing is actually to calculate the velocity structure function similar to what Yuan did. So this is, I think, like with that kind of resolution in the central region, this would be very interesting to see like how like the velocity structure function going to differ between like the hot and cold phase in these simulations.
Chris?
So a very qualitative question about morphology. So I'm struck by the fact that this sort of full class of models that we've all been running, and including my own that I've done in the past, they never actually look like real radio galaxies. They're far too long and skinny. Whereas, for example, you look at Perseus, and it's dominated by big fat bubbles there. You look at Cygnus A, again, it's pretty fat bubbles. So the aspect ratio appears to be generically wrong in a lot of these models. And there's been discussions of what we're missing. Maybe we're missing viscosity, which prevents lets you grow the bubbles beyond, but it seems that we don't miss viscosity. Irina's shown us that. Maybe magnetic tension has been letting the bubbles blow without disrupting through Rayleigh-Taylor, but you've got magnetic fields in your models, your very nice models. So what are we missing? Or am I wrong?
We should probably talk about that in a couple of months from now. Like it's a good question, and yeah, we don't have an answer to that yet. And like as I mentioned, like the everything I showed you was just like inside that tiny part. So we haven't did like a careful analysis on like how like the bubbles eventually, like how far they're going to rise. And so like in the video, like some stuff leaves the box. So this is like the 100 kpc from the center. So stuff leaves there, but we haven't traced it yet.
Okay. We I'll want to get follow up, and I'll let Mike go.
Chris, I'm so sorry. We have more people. I'm sorry to cut you off. I just want to be fair to everyone. We have about 5 minutes and 4 minutes and 4 people. So please try to keep the discussion, question, answer each to 1 minute. 1, 2, 3, 4.
You showed the structure of flux tubes, actually, vortex tubes. Then you did the decomposition and what you call the shell decomposition. Can you maybe show this picture? So one doesn't have this picture of eddies that turn into smaller eddies. One has a picture where one has long tubes, and each of the long tubes encompasses all the scales. The length of the tube is the large length scale, and then the smaller scales are the encoded within the tube. That's the picture that you saw in the undecomposed picture. And then you said when you do this decomposition, yeah, exactly. On the top you see these tubes, right? Top left.
Yes.
That's the original structure. So what do you then learn from decomposing it? You said you learned something from this decomposition. So what is it?
Oh, like for example, if we look at like so. This is kind of confirming if you say like the cascade is highly local. If we would have non-local transfer, then something here would show up. Yes. And if we, for example, look at the magnetic tension term, then this is also still local, yes. But it's
from the picture itself, you don't actually see that, or do you see that from the picture?
I'm so sorry to cut you off. Sorry. Next, please.
Thanks, Phil. Like I always tell you whenever we meet up, I really love your work. So I'm wondering if you're doing full isotropic shells for your global simulations, and if you are, is that the right choice? It feels like these have cylindrical symmetry.
Yeah, so like this is the, like to calculate this, it's like the most simplest approach. We just take the box and we don't even use any windowing because like for the FFTs we throw in there, they assume periodicity. Mm-hmm. Fortunately, given that our cluster is like kind of like periodic if you take the center,
sure.
So we don't even get like noise.
I was kind of actually thinking about your shell-to-shell analysis. If you're doing spherical shells over a cylindrical structure, you know, what kind of artifacts might you expect?
Also a question to take offline.
Thank you. Please go ahead.
So it's still surprising to me, I guess, the result that you can match a ILES to a DNS and sort of get the same sort of power spectra at least, because the numerical dissipation, of course, doesn't act similarly at all to how the real dissipation works, and in particular, it varies throughout the domain, right, depending on the local structure of the flow. And I was wondering if that has any consequences for how the energy transfer works, or have you thought about that at all? And also, have you thought about trying any way of measuring the dissipation locally in the simulations? Sorry, it's a really.
So we haven't thought about like the local aspect, but from a global aspect, if you look very carefully, like we didn't account for 100%. So our peak numerical dissipation was slightly offset from the one that actually should have been there. So therefore, I would say that's like a 0th order approximation to like it's still numerical, so it's not physical, but apparently it's close enough to get like at least for the quantities we are interested in, it's close enough to actually represent it to like.
On this note, I'm sorry to cut this discussion off. Please, one last question.
Very quick question. So in your shell-to-shell analysis, how do you define the kinetic energy spectrum?
You know this.
Okay, we're taking this offline. Thank you so much. Let's thank the speaker once again.